All right. Hi, everyone. Welcome to the USACO Bronze and Silver CPI and XCamp workshop. In this session, we'll be going over the bronze and silver questions from the USACO February contest. And for the USACO Gold solutions, we'll be going over them in the workshop in the afternoon.
Okay, so this is bronze problem 1.
Wait, sorry, I think this is the wrong slide. Okay. So this workshop is co-hosted with our sponsor, XCamp. XCamp Academy is a Silicon Valley-based institute that offers coding classes for middle and high school students to achieve success at contests like USACO and beyond. And we'd also like to say thank you to XCamp for providing us with the discount code CPI 100. So if you're signing up for XCamp classes, you can use this discount code. And for the schedule of the workshop, for the first hour, we'll be going over the bronze problems and solutions. And for the second hour, we'll be going over the silver problems and solutions. We'll have teachers from both XCamp and CPI be teaching. All right, so now we can get started with the first problem, which is sleeping in class. Jesse, you can screen share so you can use your whiteboard.
Wait, can I just explain directly from the slides?
Oh, that's fine too.
Okay, yeah. Okay, so basically this is the first problem, and it's called sleeping in class. So as Maggie said, so you're basically given an array of length n, which is, and the maximum array element is 10 to the 6th, and basically what you're trying to find is the minimum number of operations to make each element in the array equal in linear time. And in each operation, you can combine elements I and I plus 1, so 2 consecutive elements basically. And it's guaranteed that the sum of A doesn't exceed 10 to the 6th, so that might be important. So here are the sequence of operations in the first subcase of the sample. So the initial array is 1, 2, 3, 1, 1, and then it becomes 3, 3, 1, 1, 1, and then becomes 3, 3, 2, 1, and then 3, 3, 3. So we can see here that it requires a minimum of 3 operations to make the entire array equal. All right, so basically the solution to this problem is basically, it requires a key observation, which is rather than trying to simulate the operations, we can notice that after each operation, the sum of the array stays the same. So suppose that there are X elements remaining in the array, and the sum of the array is S. Each element after a set of operations will be exactly like S over X, which is where X is like a it's like a possible candidate for the number of elements remaining. So X can only be a divisor of the sum S in order for it to work. So basically, you want to find the maximum value of X by iterating over the divisors of S and checking whether the array can be combined in such a way that each element is equal to S over X. And basically, the answer is just n minus X. And you can find my code on the official USACO website. So yeah.
Okay, thank you, Jesse. The next problem will be by Brendan. You can screen share.
Oh, okay. I think there was a question in the chat though about the previous one. Should we answer that first? Oh, okay. Jesse's answering it. Okay, great. Sure. Why don't I share my whiteboard and we can get started. Okay, so I'm going to be going over the second problem from the bronze competition this time. And this one was called Photoshoot 2. So we've seen many Photoshoot problems in USACO before. This is another one that's similar where we have cows and we're moving them around. Okay, so what are we given? We're saying Farmer John is lining up his N cows. So we have a bunch of cows and they're conveniently numbered 1 through N. So 1 all the way to N for a photograph. And they have some very specific order. So they're going to give us that order. And that order, it says, is going to be A1, A2, all the way up to AN. Okay. From left to right, the order that it's being given to us. And what we want to do is we want to put the cows in the order B1 to B2 all the way to BN. Okay. So we have this sort of position of where the cows originally belong, and we have a position of where we want the cows to end up. And it's our job to figure out the minimum number of modifications required in order for Farmer John to line up his cows in the desired order. Okay, so again, we're trying to minimize this. So let's jump right into the sample cases here to see if we can understand how it works and maybe create a strategy on how we can solve this. So the first line of input is a number that's telling us how many cows we have. And then the second line is our first order. So I'm going to call my first order A here. And we have the order 1, 2, 3, 4, and 5, which is just the same as the cows in order. They didn't move at all, okay? And what we're trying to get to is this order B, which means that the cows are in positions 1, 2, 3, 4, and 5. Now, what I can notice immediately is none of the cows moved, right? In this case, we didn't have to move around any cows to get to my desired order because they already were in the desired order. And so there was no work for me to do. So again, what was the problem asking me to do? My task is to print the number of modifications required to produce my intended ordering. I already have my intended ordering. So here I don't need to do anything. And so the minimum amount of work I have to do is 0. Now I could have moved things again around, but remember, again, the task is to find the minimum amount of work in order to get the order that I need. So that test case was a little bit on the simple and boring side and maybe not super helpful, but the next one is going to give us a lot of really good information that's going to help us to understand exactly how this problem works and will hopefully give us some ideas. So let's look at the next one here. The next one, again, has 5 cows. And they're in the order 5, 1, 3, 2, and 4. So this is what I'm working with here. And now my desired order of how I want them to be here, of what they should end up in, is in the order 4, 5, 2, 1, 3. So this is not the same as the first test case. Obviously, I can see that they are not in the exact same positions. And so that's I can't just do no work here. So I'm going to have to do some swappings. So when I look at my original list here, this one here, and I ask myself, what really needs to be moved around? Well, one thing I may notice is I notice that in my top ordering, I have 4, which is comes after 5. But in the order that I want it to be in the end, I notice that 4 comes before 5. So this is something that's telling me, hey, I'm going to have to swap some numbers around because I'm not going to get the right ordering, just leaving it as is. Also, when I look at 2, I look at 2 and I look at 1, and I compare them to the ordering of how the output should be here. And I notice that those are also reversed, right? So there's some cases here that are in order that makes sense. For example, I have 5 and 1. Here I have 5 coming before 1, and those are okay. But what I notice is that there are 2 cases here that are out of order, right? The 4 and the 3. So let's just see how that would work if I were to actually swap the cows in practice. Well, what I would do is I would take the last cow here, 4, and I'd put it at the beginning. Actually, why don't I give myself a little bit more space here? I'll take that cow 4 and I'll put it at the beginning. And now I'll get something that looks like 4, 5 still remains, 1, 3, and 2. So I did that swap. I moved the 4 all the way to the front there so it can go in front of 5 like it's supposed to. And then I look at what's missing here and I can see that my 2 is still out of place. It looks like it belongs in between 5 and 1. So I'll move that one there. I'll show you what it's going to look like between 5 and 1. And what we'll get is something like this: 4, 5, 2, 1, 3. And so that is the minimum amount of work that I need to do in order to get to my answer. And so that's why you can see from the example that the sample output should be 2 here. So the key observation that we're going to make in this problem is that when we see pairs of numbers, and pairs of numbers are really important, that are in a specific order in our starting positions, but they're swapped in our ending positions over here, this is a situation where we're going to make a swap. So the first way of sort of approaching the problem, and is not the most efficient way, but for me, it's the one that makes the most sense in terms of getting to the solution, is to simply say to yourself, okay, well, I have my lineup here. I'm going to have a loop that's going to hold an index of position of my cow. And then I'll have another loop, like an inner loop, that will control the second position of another cow. And what I'll do is I'll compare them. And I'll make comparisons. So I'll show you exactly what that looks like. So here, I'll look at 5 and I'll look at 1. And there's no need for me to move my my cow I here because my ordering in the end is actually how it needs to be. Now, when I look at cow 5 against cow 3, again, my ordering matches how I need to be in the output. So there's nothing for me to do there. When I look at the next ones, though, when I look at 5 and 2, I can see that the order is okay here. And when I look at 4 here, I can see that the order is not correct. And so 4 needs to be changed. So I'll continuously loop doing comparisons between some fixed position and another, and I'll check to see if its position in B is of the first one is greater than the position in B in the second one. And if that's the case, then I just need to mark that it's going to need to be swapped. So after I go through, I can see that I have 2 of these that need to be swapped, and that is the answer for the problem. Now, the performance of my code here is not really as good as it can be, right? So I'll need an outer for loop to control the, let's say you call it I, for I, which is going to be one position here. And then I have another loop in here for J. And then once I have those 2 for loops, I'll need to have another loop inside as well, which is going to help me find the position B. So I'll need to have 3 nested loops. So another nested loop as well, which is going to slow down my code. So the next approach that we can do to make our code a little bit faster is not quite as obvious. Actually, let me scroll down here and show you what that first one can look like. Like I said, here's just taking our input, but the main chunk here is what we're doing. We have our outer loop, which controls our fixed position. And then we now have another one, J, which is moving. And what we'll do is we'll check if A at position I is greater than the position in B, which again, we're going to have to use another loop in order to find it, then we have to mark that one as moved. Okay, so that's how that first option works. So, okay, if we, we can do that and we can get to the answer using that solution, but how can we speed it up? So actually, let me write down my sample case again. So I had 5, 1, 3, 2, and 4. That was my, I'll call it A. And then I had my desired output, which is 4, 5, 2, 3, and 1. So another option is, and this is kind of hard to get to. So if you didn't get to this answer, it's definitely a very clever trick, is to say, hey, why don't we try and get B to some, I'll call this one new B here, new B, to a sorted order, 1, 2, 3, 4, 5. And then what we can do at the end is, as long as we change our A to match how it needs to be in relation to our new B, then all we need to do is we need to check to see if it's in sorted, if the order is matching up. So in sorted order. So essentially just sorting. So how are we going to do that? Well, I'm going to have to check my B positions where they are and see in relation to my new B here. So why don't I write above, I'll create a new one up above right here of how things are going to change. Okay, so the first one, it's 4 and 1, so we'll get 4. Actually, let me write them all down and then I'll show one more time. 4, 3, 5, 1, and 2. At position 4 here, oops, reset. At position 4 is 1. At position 5 is 2. So you can just sort of see how I'm matching them up like that, hopefully. But I need to take one more step where I need to modify this further. And so this is my, I'll call this my new A. And what I'm going to do is I'm going to map these two. So let me first write these out. So my new one is going to be 2, 4, 5, 3, and 1. So what I'll do is I'll check at position 5. At position 5 here, let me highlight that, is 2. So at position 5, I'm checking that one is 2. So that's how I'll put that over here, and I can fill those out for the rest of them. So that's the hardest step of this solution, is switching them around so that they're in the appropriate order, so it matches up for my new sorted order. And then all I have to do is I have to check and make sure that all the items that come before it are less than what I'm looking at. So here is the work that that is happening to create that first ordering from above, this one up here. And then I switch it around as well in this one here. And then what I can do is I can simply use 2 loops here. So I'll loop through and I'll check to see if I need to move my J. And if I see a position that comes before J that needs to move, then I can set that to true in this instance, and mark that one as need to be moved. And if it needs to be moved, then I can increment my answer. Now this one is better than the first solution because I only have to have two nested loops in here instead of 3. And so I'll have improvement in my solution. And then to optimize it even further, if you wanted to, instead of having to have this inner loop here, where I need to loop through and check all the items that come before it to see if I need to move J, I can simply keep track of the maximum value that I have seen before J. And as long as I keep track of the maximum value I see before J, then I can do this comparison here and I can know if it's necessary for me to move, if I need to move J or not. And that will help me to understand if I need to swap. So I've started with 3 nested loops. I did a little trick to get them in sorted order instead. And once I did that trick to get them in sorted order instead, I was able to get rid of my innermost loop. And then if I keep track of the maximum value along the way, I can improve this code as well in order to just have one loop along the way. And so that would be my O of n solution, and that's the best we can find. Okay. All right, so I'll stop sharing and we can keep going to the next problem.
Okay, David will be presenting his solution to the third problem, so you can try sharing.
Yeah. Everybody, everyone can hear me all right, right? Like, good stuff. Oh, yeah. Everyone can hear me, right?
Yep, we can hear you.
Yeah, cool. So today we'll be doing bronze 3. And so I'll just give like a recap what the problem statement is. Basically, you're given n words and 4 blocks, and each block has 6 sides, so 6 possible characters. And your goal is to make it so that you can configure the blocks such that they make certain words or your n words. And if you can make the block or can make the word out of those blocks, you print yes. And then if you can't, you print no for each word. For example, in the sample input, right, we're given 4 dice, or not dice, blocks, each with 6 characters representing 6 sides. And so for the first word, for example, like cow, you can make the word using block 2's C, block 1 or 2's O, and then block 3's W. So basically you can select each one, or like you can select each like face of the block as a possible letter to use, and then you can write, or yeah, then you can construct your words as you want. For example, you can't make the word moo because you can only use 1 block at a time. So even though we have the letters to make moo, M-O-O, we can only use 1 block once. So if I were like this first block or the 0th block is the only one that contains an M, therefore like we can't use it anymore. And there's no other blocks with 2 O's. So yeah. So the idea here is, this is kind of the setup, right? We'll construct a 2D array of Booleans of size 4 by 26. So I called it contains char. If you're using Java, you can use, like, you have to type in Boolean fully. But yeah, so there's 2 parameters, I, which goes from 0 to 3, and then j, which goes from 0 to 25. And the first parameter will represent one of the 4 blocks. So you're only given 4 blocks, and you check at the ith block. And then the 0 through 25 will represent all 26 letters of the alphabet, saying like, at this block, does it contain this letter? That's the basic idea of it. So yeah, and then this is 0 indexed. So this is why it's like 0 to 25 instead of 1 to 26. But if you want to check whether a block, like whether block I contains letter J, you just ask, does contains char I, J? And then if it's true, it contains the letter, and if it's false, it doesn't. Okay, that's the main idea. Here's kind of what it looks like. So this is just the beginning. I'll show you how I set it up later. But this is just imports as like standard library. And then I use long a lot because I don't want to avoid integer overflow, but it's not a really big deal in this problem. But yeah, so the main part is I'm going to have a 2D array. So maybe like in Java, like array list, double array list, but 2D vector of Booleans, and I called it contains char. Size 4 representing each block, and then 26 representing all 26 letters of the alphabet. And I'll first set it to false. So then in order to initialize contains char, what I'll do is I'll take my strings as input. So first I input like the n words, that's just required. And then I'll input each string, and then I'll iterate through each string saying that, hey, at block I, or yeah, so there's 4 blocks. And then at block I, or wait, sorry, these strings represent the blocks. And so for each block, I'm going to iterate through all of them and say that it contains the letter. And what it does is this kind of part, s square bracket j minus letter a, it converts the character to an integer from 0 to 26 or 0 to 25. And so a would represent 0, b would represent 1, c would represent 2, and then so on and so on. And so it converts it to its ASCII value. And then this way we can keep track really quickly whether that block contains the correct letter. Okay. So this is where it kind of gets a little tricky, but in order to solve this problem, we have to use a little bit of recursion and what's known as backtracking. So I have the blocks on the side here, and then I have like kind of this really nice MS Paint graph. But first off, whenever you're using recursion, or you can think of this problem as like taking recursive steps, and whenever you think of recursion, you got to think of it as some sort of like tree. This will be very prevalent in like higher level problems, but this is like trees are pretty important, and this is a pretty tough problem. So here I got the word cow, and I'm gonna have a bunch of levels to this tree, okay? And each level will represent a certain letter. For example, the first level will represent the C in cow. The second level will have the O in cow, and then the W will be like the W in cow. And so here I have like this curly bracket saying of all the blocks. And remember, I can only use each block once. So yeah. So first I'm going to go through all the work, like the blocks, seeing whether it contains the correct letter. For example, in this first level, we're going to see if it contains the letter C. And we see that in block 0, there's no C. Okay. And we can check this through our contains char array from before, right here. But I'll go into the code later on after this. So for this, in block 0, it doesn't contain the letter C. So I'm going to put an X over it, and I'm going to stop. I'm going to stop. Like this tree has a bunch of paths, and then I'm going to stop when it doesn't work. So this red X symbol means I don't have the correct letter. I'm not going to continue on. Here, let's see, block 1 doesn't have the letter C. Block 2 does have the letter C right here. So we're going to put a check mark, and we're going to keep on going. But block 3 does not have the letter C. So we're going to stop here as well. And then you'll notice like you'll go down the tree. You'll have to use recursion to look through it. But every time we go through, if there's a check mark, we keep going, or check marks mean like the block corresponding to it contains the letter. And then if it has an X, it doesn't contain the letter. And so if it's a check mark, we'll keep on going. And then if it's an X, we'll just stop. And so we'll just keep on going with this example, right? So at the second level, we're talking about letter O, right? And so does block 0 contain letter O? Yes, let's have a check mark. Does block 1 contain letter O? Yes, check mark. Block 3, no. And notice how I'm skipping block 2 because we've already used it. Now I'll explain how we like code it out that way later, but just keep that in mind. You can't repeat blocks. Then at the very final level, the third level, we'll see that like block 1 doesn't have the W, but block 3 does. And so we'll put a check mark there. And then block 0 doesn't, block 3 does. And so, yeah. And so this tree will go through a bunch of different paths. But like I said earlier, if there's an X or that block doesn't contain the right letter that we're looking for at that current level, so C is first level, 0, second level, W is third level. If it doesn't contain the letter, we're not going to keep on going. We don't need to check because that situation is impossible. And so if it has a check mark, we're going to keep on going. Okay. And so what you'll notice is that if there is a check mark at the very bottom level, or like the last letter in the string, that means it works. There's a possibility. And with trees and stuff like this, recursion allows it so that we can go through every possibility and rearrange all the blocks into patterns, seeing like whether or not it can work or not, or whether or not we can construct a certain word. That's kind of like one of the strengths of recursion, but yeah. And then, yeah, so also a kind of neat fact is that the amount of check marks at the very bottom level also determines how many ways we can make the word. For example, in here, we can use blocks 2, 0, 3 to make cow. So COW. And then we can also use 213, C0W. And so that makes it so that there's 2 check marks at the bottom, or the amount of ways, but that the problem doesn't ask for how many. Overall, this recursive step is pretty tough, but hopefully it kind of makes sense. So what I did was I made like a helper method, basically just like a function that returns a true or false value saying like, does this string, well, is it possible to construct the string with the blocks? So again, I'm using this contains char array, and I'll continue on with that. And this is where we go into what's called backtracking, which it's a pretty tough topic for beginners, but you can check it out at like the competitive programming handbook. That's how I learned it. So anyways, so we're going to have a Boolean array called used, and it's going to say whether we've used the block already. Okay, notice how it's only size 4 because we only have 4 blocks. And so we're going to have 2 parameters inside our function, and it's going to be the variable s and the integer position. I just say pose because that's just short. So if you want to ask, so this is going to help us determine the level we are on, and the level or the current letter at that level is going to be s pos, or like at the character at the position in the string. Like in Java, it would be s.char at pos. And so also a pretty important fact is, just like how I said at the very end, like if we reach the bottom of the tree and there's a check mark, that means it's possible. So here, if the position of the string is greater than its length, that means we're going to return true because we have reached the bottom of the tree. And so basically, when we're going through with recursion, we're going through all the different possibilities to like configure blocks to see whether it makes the word. We're gonna encounter different like ways to make it, but if it reaches that bottom of the tree, it's gonna be true because that configuration works, if that makes sense. So yeah, it's a little confusing, but we'll get closer. So here's kind of the meat of the function where we're looping through all the different blocks and check if it's been used. For example, if this, remember, I initialized used as false in the beginning, meaning we haven't used the blocks yet. But how it's going to start out is basically when you're looping through the for loop, if used is true, this is what that means, or it doesn't contain the char that we're at. So remember, s position or s.char at for Java position is like s.char position is the current letter we're on. If it doesn't contain that current, like if the block doesn't contain that character, we're just going to continue. And this would simulate the x's that we're talking about. Basically, if it doesn't contain the character, it's going to be an x. And then if we've already used the block, we're not even going to write out the arrow, or not even going to go through that path. And then, yeah, we're going to continue. So if none of the blocks works, basically meaning like if none of the blocks works and we don't, like if we always go through this if statement, we're going to return false because, like, for example, in the back here, when we use mu, if we were to draw it out, it would lead to all x's. There would be no check marks at the very end. And so that means we would have to return false. Yeah. And then to keep track of whether we've used a block or not, we use what's called backtracking. This is going to be a little bit hard to follow, but it's okay. So so how backtracking works is kind of interesting, and it's also what helps with recursion and going through all possibilities. And so I'm going to kind of simulate it through my mouse. Hopefully y'all can follow. But how it goes is like this, right? We're going to start, and I don't think I show this in my code, but right here, if y'all see the highlighted, I'm going to call my initial call. So I'm going to take in, this S is the word that we currently are. So for example, cow would be one of the words. And then use this is making it so that we're initializing used is all false. Okay, but we'll get into it. So we're going to first call possible S0, meaning we're going to start at the first letter. Okay, so that would be C. So let's see. Let's look at C and see, like, we're going to go through all the different blocks and see if it works. So 0, we haven't used it, but it doesn't contain the correct word or the correct letter. One, it hasn't been used yet, so this condition is false, but it doesn't contain the word again, and that's an X, so we're going to continue. 2 contains the correct letter, and it hasn't been used, so we can go down the tree. And so we're going to put a check mark there. There's no like actual check mark function, but it's just a good way to like visualize it. So then what we're going to do is say like, hey, we have already used this block. We're going to set this to true. And then now we're going to take a recursive call down the tree. And then we're going to move to the next letter. So that would be O. That's what this position 1 + 1 is doing. Okay. And so we're going to look through each of the letters and say like, or we're going to look through each of the blocks again. And so with recursion, we're going to go back up here and start all over again, except the position is now going to be 1, or it's going to be for letter O. Okay. So we haven't reached the bottom of the tree, so we're going to ignore this if statement, but we're going to go back to the for loop again. Hey, have we used it? Have we used the word O, or I mean the word 0, or block 0? Have we used block 0? No. And we also have the correct character. Okay, this exclamation point means false. So if we don't contain the correct character, it's going to return false, and then it's going to switch to true, but whatever. So we have the correct character for block 0, and we haven't used it yet. So we're going to continue and say, we're going to put a check mark there and say like, okay, we've used it. That's true. And then we're going to keep track of that. And then we're going to go down the tree again. Okay. Then for the for loop, right, we'll see. Okay. We're going to look through all the blocks again and say like, hey, we've already used block 0. So initially it starts at 0. Since we've already used it, that means this condition is false, and we won't go through that path, but yeah. Block 1 does not contain the letter W, so it's going to have an X, and then block 3 does contain that. That's kind of how it works. And then with backtracking, what it does is before you recurse down the tree, we're going to say that we've used it so that in future recursive steps, we're not going to reuse blocks. And then after, when we're done, we're going to pull out and then not use it anymore. Backtracking is a pretty tough topic, but yeah. What's the point of having a bool possible instead of just DFS by value? Having bool possible instead of DFS by value. Wait, I did a Boolean because it tells us whether it's possible or not. Like, it only returns a true or false value. And then if it returns true, that means the word is able to, like, it is possible to construct the word with the blocks given, the 4 blocks. You don't have to count how many configurations there are. You just need to say like, is it possible or not? You only need to print yes or no. That's the point of having Boolean. Yes. Okay, so, no, I don't. Okay, so I'm gonna go through the code like one more time. Yes, you can use the next permutation function, which actually does a lot of it for you, which I think what you can do, let me just quickly try this out. You can do like a do while loop where next permutation. So the string would be string.begin. Or wait, actually, we have to go through all the blocks, but okay, wait. This won't take too long. Yeah, whatever. So what I'm creating is a vector that represents each of the blocks. And what I can do, this is a different, anyways, so what next permutation does is it creates like different permutations for you as well. And it configures the blocks in all the different ways. And basically, if the first 3 blocks that you rearrange like, for example, a permutation would be like 0, 1, 2, 3, and then another one would be like use 1, 0, 2, 3. And so you can go through all the different ways and check whether the first 3 blocks matches to a cow. If, like, yeah, whatever, I'm not gonna waste too much time. But yeah, but yes, there is a solution with next term permutation. I'm sure it's on the USACO website, but yeah. This is basically it. And then this possible function, like I mentioned earlier, only returns a true or false value. And if it's true, that means we print yes. If it's false, we print no. And then, yeah, we go through each word and see if it's possible or not. Yeah, I think that's it for me. But thank you for listening. I hope you enjoyed, and recursion is fun.
All right, thank you, David. So now we're going to move on to the silver problems, and we'll have Ryan start.
Okay, so I'll be doing silver problem 1. So basically we're given like n cows, and then each of them are assigned like gift I, and then afterwards we're given n permutations of 1 to n, and we define like the earliest possible element in the permutation given to cow I, such that each cow must receive a gift less than or equal to indexed to the present 3 zeta set. So they need to receive a gift ahead or equal to I. And then the input is just n, and then the next n lines are the permutations. And here's a sample input. So we have 4, which is the number of cows, and these are all your wish lists. So let me see if I can do like, okay. So like here, this signifies that like cow 2 would rather have present 3 than like present 2. Okay. And then the reason why the output is 1, 2, 2, 4 is because like it's impossible to give cow 1 a better gift, because she wants like gift 1 the most, and she got gift 1. And then if she didn't get gift 1, then like she couldn't choose a gift otherwise, because it has to be like better than or equal to 1. And then yeah, so in this, the second cow acts as a choice. If she takes gift 3, then this third cow would take gift 2. If she takes gift 2, then the third cow would take gift 3. And both of these work because in the first case, you're taking like a present that's not yours, and then another cow is taking your present. So like no gifts go unassigned, and like all of the elements are like in their correct positions. Or we can just go back to like to just like choosing your gift that you set out with. So it says 1, 2, 3, 4. And obviously this cow would rather have 3 than 2 because they want it more. So that's why the output is 1, 3, 2, 4. Yeah. And the same thing for 4. If we give cow 4 another gift, then like some cow like here wouldn't have a gift to choose. Okay, so like we can just like build a directed graph where there's an edge between I and j for every gift in cow i's wish list with an index less than or equal to I in the wish list. And the reason why we can just ignore everything after I is because it will never create a correct rearrangement. So we really don't care about that. And yeah, so here's the graph for the sample input. So 2 wants 3, and then 3 wants 2. And then like every node also has a self loop because they also want their own gift in like the worst case. And yeah, so like in the actual graph, there'd be self loops, but I didn't draw them because it take up too much room. Yeah. And then we can only swap gifts when there's a cycle between the target gifts. But like, why does this work? Because whenever we take a gift from another cow, like the cow needs to, like the cow that we take it from needs to have a gift which it can take like in case, because that cow took like their guaranteed backup gift. So that cow needs to have like a different gift that I can choose from. So now we find a cycle. Each cow can take the next gift on a cycle. So if we have like a cycle for like 2 or more cows, then like we can assign every cow on the list like the previous gift. And then every cow and like a current cow will obviously get a better gift because we have um because like we because there's edges between the gifts that they want. Yeah. And we can just like DFS this and then like go to all possible pairs. So we're just going to use a DFS to find all the cycles. And then the way we do that is not like implicitly, it's kind of just using like kind of a weird trick to do it. Yeah, but like once you see it, it'll be like pretty easy to understand. So yeah, so a DFS to find cycles will take O(n), and to like DFS for all pairs, it'll take O of n cubed time. So that's like, that's the explanation. And then I'm also going to send a link in chat. So if you want to look at the code on your screen, you can do that as well. Okay, so here's the code. Yeah, so like here's an input. So for every, it's like for auto permutations, we're going to read in a gift and push it back to this perms array. I'm going to push back minus gift because in this case, we're doing it all 0 indexed. You can like change it to make it 1 indexed, but yeah, it doesn't really matter. And then if the gift is I, meaning that like we've reached a point where like we can't take any more gifts out of this, that'll create a valid rearrangement. We're just gonna reinvest the gifts and break. Yeah, and this is gonna be like a visit array. So this is gonna store like whether if okay, so like so visit to ij means that like means we can go from cow I to cow j. And yeah, so like this is not, we're not explicitly searching for cycles, we're just finding paths between them. So here, right now we're just doing like a BFS, but you can also do a DFS. And so you just change this for the stack if you want to do a DFS, but like it really doesn't matter. And you can also implement this recursively. This is implemented iteratively. Yeah. So whenever it's like each pair incurs gonna store which cow we came from and the cow we're currently from, because this will help us like construct like a valid graph, like help us construct a valid path. Yeah, so next is just gonna start like a current cow, and then if we visited this cow already, then like we're just gonna continue because we don't want to revisit cows that we've visited already, because this will probably cause an infinite loop. And then here we're just gonna set visited true, meaning that there's a path from next dot first to next dot second. And then for all of the cows, for all of the gifts that cow next dot second wants, we're going to switch to them as well to next dot first, because next dot first is the cow that we came from, and then U is going to be like a next cow on that path. And here we're just going to like all of the possible pairs. And then if we visited gift I, then it means that there's a cycle, and we just output the gift. And note that like the question kind of makes this unclear, but the output doesn't have to be a permutation of n. It's just whatever the optimal for the current cow. So you don't need to consider other cows. And yeah, so the trick that I was talking about is here. We just set visit to like a root to a current node as true, but obviously like if there's a path from like 1 to 2 and there's a path from 2 to 1, then like that's a cycle. And that's like, and that's how we use this visit array to like find these cycles. And yeah, so that's about it. And I give it to the next instructor, which is, I think, Kevin.
Yeah. So let me just share screen. All right, so now we're moving on to the second problem in the silver contest. So they give you like 40 points, and for each relevant number k, outpoint the number of point subsets of size k that add up to another given point. For the example input, I have that here. But I feel like this is just a kind of weird problem in that the bound is n equals 40, which only happens in like once in a blue moon. Now, sometimes in a gold contest, n equals 40 to 50. This can mean a bound like n to the 4th or n to the 5th, but those complexities don't seem right for this. Just you get a gut feeling that those complexities wouldn't be applicable to this problem. Now, the only complexity that would seem even remotely possible would be 2 to the n. But how would you do that? Because 2 to the n is only possible when n is less than or equal to 20. Now from that, you go to 20 equals 40 divided by 2. So maybe let's try splitting the points in half, and then let's go from there. So after this, you get which I feel is a pretty intuitive solution, which is you split the points in half. See in there for a second. So for the solution, you just split the points in half. What criteria you use to split doesn't matter. You just have to end up with like maybe a 4 and a 3, maybe, and if they gave 31 points, maybe you could split it into 15 and 16 points. But that doesn't really matter how you split them, as long as it's just generally split in half. And for each half, you calculate the sums of all the subsets of those points. And then you can group the subsets by how many points are in that subset. This is for a specific implementation. And here's a small example. Well, so let's say we only had 4 points and one of the halves was like this. And if you had this subset of points, you end up with these 4 subset sums. You have the empty subset, which resulted in 0, 0, a subset of size 1, which just resulted in these 2, and a subset of size 2, which is just these 2 combined together. And then for each possible pair in the first set, you match it up with every other size in the second set. And if a matching point exists, increment the corresponding total. And this is possible with a multi-set or map. There's also one that involves a 2-pointer solution, but I feel like the map solution is just a bit more intuitive and easy to implement. And this ends up with a final complexity of 2 to the n divided by 2. This divide by 2 is important, as a normal 2 to the n would actually TLE on the grader. And there's also an additional linear factor, but this still should have it run under time. So this is the code right from the USACO website. I felt like it still does a good job of implementing the hash map solution. So at the top, we have some point functions. You can add points, you can subtract them, just some standard utility functions. And this gives an all sum. This function, all subsets, it returns a vector of points and integers. So this returns a vector of all the possible points that are achievable. All right, hold on some functions. So hold on some questions. Sorry, I didn't see the chat. 1, 3 comes from adding 1, 1 and 0, 2. And oh wait, try and answer that already. How would it be 2 to the? How would it be 2 to the n divided? No, be 2 to the n divided by 2 squared. Could you elaborate on your question a bit, Max? And as for Eric's question, it doesn't matter. Like I said, it doesn't matter where you split it in half, as so long as it's split in half. It doesn't have any impact on the final solution. Yeah, but we're only iterating through one half. And using a map for the other half, we can automatically automatically match it up to everything else in the second half. Yeah. It does have some impact on the constant factors. There is a solution with 2 pointers, but that requires some, but that's just a more elaborate implementation. So more questions. How does that work? We just read in half the input into one vector and then half the input into another vector. So as you can see, this code calls all subsets on one half of the vector, and then it calls it on the later half. And it stores them in A and B respectively. And then it makes A into a map, like I said earlier. And then this code just iterates through all of B and finds the corresponding points and sizes in the unordered map here. And the custom and this is just a custom hash because default C++ unordered map is stupid slow. Like I think it's a couple of times slower than even just normal map, which is actually n log n. So because of the custom hashing. So we just implement a really quick O of 1 hash. And that should make it so that unordered map can have the program run in time. And then after that, we just increment ands by all the relevant ways. Then after that, we just output everything in the answer vector. So any final questions? 2 moves. Oh yeah, that's what this code does. It like matches up the stuff in A with the stuff in B. It's like it iterates through everything in B, and then it tries to find stuff in the first half, and then it iterates through everything there. Which section in particular? Or is it, do you just need a whole overview again? All right, so I'll just go back to the slides. So actually, I'll do a walkthrough of the code again. So first off, we read in all the points. This is standard IO work. And then we split the vectors. We split it in half. We split into 2 vectors, A and B. Now A and B, so what's 2 to the A and 2 times 2 to the B? The total complexity, you mean? It's actually just 2 to the A plus 2 to the B times 2 to the A plus 2 to the B plus, wait, let me just, times 2 to plus 2 to the B times some linear factor here. But we only take the largest factor in time complexity, so this is the defining time complexity. But back to the overview. Offset is all the possible points that we got from A. Offset is just the sum of the subsets. Does that answer your question? Anyways, all right, good to hear that. So then we have A and B. These are the all possible subset sums of the first half and second half respectively. So let's see here. So A would have, if we use the example input, A would contain all the subset sums here, and B, actually no, A would contain all the subset sums of these 4 points, and B would contain all the subset sums of these 3 points. And then we make a map from A. So first half, it gives you all the possible, sorry about that. It gives you all the possible offsets and subset sizes. Num is a bad variable name. I don't know why they chose that. It's more of a subset size. So first half offset subset size will give you the number of subsets that fulfill that requirement. And then we go through all the possible offsets in B. This map just number of operations, the points achieved. Actually, no, it's a 3D map, so you have to give it two things for you can give it the target point of the subsets, and you also give it the subset size, because the answer also asks for each individual subset size. And then we go through each possible point in the second half, and then we match it up with the stuff in the first half. So first half, we try to find the offset, and if it exists, we go through all the possible subset sizes in that target point. Then we increment the answer array accordingly. So are there any other questions? All right, then that's it for me. I'll be passing it on to the final solver problem 3 instructor.
Okay, great.
Okay, we'll have Brendan do the third problem now.
Okay, why don't I share my screen? And we can talk about this last one here, which is email filing. Okay. All right, so how does this one work? Basically, it's Farmer John is having his emails on his screen, and he wants to organize them in folders. And his task is to sort of scroll through all of his emails, putting them in folders, in the folder it's supposed to go into. And sort of the caveat to this problem is that you can only scroll down, you cannot scroll up. So there's a lot of sort of moving pieces and difficult things to understand. So let's start breaking them down and understanding how it works. So the first thing I wanted to do was I wanted to draw the screen so you can sort of picture what's going on here. And it says that it's broken up in half here. So on the left side, what we're going to do is we're going to have a bunch of files. So here I'll label it files. So this is file 1, file 2, and our files are labeled, or folders are labeled from 1 to M. So these are, I'll change this to folders. And on the right side, what we're going to do is we're going to have all of our emails. So here are our emails in this section, and those are from 1 to N. So 1, 2, all the way down to N. Okay, so with these emails here, what we're going to be given is this number, which is F sub I. So F sub I is going to tell us the folder that it needs to go in. So really, instead of putting the emails 1 through N, those 1 through N emails, we can instead place their numbers. So for example, let's say it was 5, 6, 2, 4, something like that. That would just mean that this email here needs to go in the 5th folder, which is somewhere here. This second email needs to go in folder number 6, which would be somewhere here. This third email needs to go in folder 2, and so on and so forth for all of the emails that we have. Okay, so there's two more tricks that are going on to this problem here. The first one is that we have this value, which is K, and K represents how much he can see on the screen. So we can almost think of this as like, this is the real screen, right? Let's say it's like, this is the real screen. And in order to see all of the emails in all the folders, he would have to scroll down. So he could move this blue window down and he'd be able to see other folders and emails. But remember, his mouse is broken and he can't go back up. So that's the important part. So we can We can scroll on the emails, we can scroll on the folders. So that's important to understand. The other thing that's important to understand about this problem is, let's say we have an email. Well, let's say this goes to 2, this goes to 3, this goes to 1, something like that. In order to file this email, the folder needs to be in the window that we're seeing right now. So the window is that blue box. So if I can file that email, it needs to be in that window. And also when I file that email, it means that it's going to disappear, like in the way that emails would really disappear. And we can imagine the rest of them sort of follow up on the screen, just like they would in a real email. Are the folder and email scrolls independent, or do they scroll concurrently? Yes. So yeah, it's not super clear by the problem, but yes, we can scroll independently, and we'll see how we have to do that. But again, like I said, it becomes complicated by sort of filing emails, and then the new emails will fill in place there. Okay, so it works kind of like, I guess, cleaning out your real email inbox would work. Okay, and yeah, so one thing that the problem says sort of towards the end is that, there's no scrolling up, but there is this case where, let's say you're viewing the last K emails. Let's say that your window is something down here. You're viewing these last K ones in here, and you end up filing one of them. Then let's say file the one at the top. Then remember, they automatically repopulate. And so that's kind of like a semblance of scrolling up, is if we're in our last K emails that haven't been filed yet, and we file one of them, then it's almost that appearance of scrolling up, because we're able to reach an email that was previously skipped, that was previously scrolled on. So that's our only way of scrolling up, but I wouldn't necessarily call that scrolling up. But let's look at the sample case all of the sample cases to understand how it works. So for the sample cases, what it's going to give you is it's going to give you this this number T, and T is our number of subcases. So usually when you see this, it's going to it means that you're going to do this process of whatever you create T number of times, which could add some complexity to your code. But in this case, if you check the input format, it says it's guaranteed that the sum of M over all subcases does not exceed 10 to the 4, and the sum of N over all subcases does not exceed 10 to the 5th. And so we have a little bit more clarity as to all the M's and the N's over all the subcases there. So that will help us understand exactly how big our solution will be for some specific test T. So let's go through some of them and make sure we understand how it works. So the first number was 6. That's the number of test cases. The next thing I'll do is I'll write down these numbers 5, 5, and 1. So what do those represent? Those numbers represent M. So M, we said, were the number of folders, and remember, those are going to be 1, 2, 3, 4, and 5, right? And then what we have is we have the number of emails. So emails, and these emails, each email, we're basically going to have it represented by its some f sub I number, right? And that number is going to tell us where we need to file it. It's our filing number. It needs to go in a specific folder. And then our last number here is our number K, which K is not very specific. I'll call it screen size. So screen size will help us to understand how much of the screen we can see at one point in time. Okay. So given those numbers 5, 5, and 1, And then our next line of input is, I guess, why don't I draw the screen here, and I have my two different ones. Remember, in my folders, I'll have 1, 2, 3, 4, and 5. And then for my my filing positions of where each of the emails need to get filed is also 1, 2, 3, 4, 5, like this. Remember, k is equal to 1 in this example, which means that although this is what I've drawn, you can really picture Farmer John's screen looking something more like this. And this is what he will see, okay? So at the beginning, what we have is I have file number 1 on my left. I have my email that needs to be filed in folder 1. So this is perfect. What I can do is I can take this email and I can file it in this folder. And then remember what happens is this one will disappear. And then the next one will jump up into our view. So we have 2, 3, 4, 5, kind of like if you were deleting or moving files from your email. Okay, so now this is what we see. We see our email that needs to be moved to file 2, but all we're seeing right now is the folder 1. So we can scroll down, and now our perspective, actually, maybe it's easier if I draw an arrow. Now our perspective is folder 2. And so I have folder 2, and I have my email that needs to be filed in folder 2. And so that one can be removed. And like I said, I'll just draw arrows so I can draw a little bit faster. So now I'm viewing folder 2 and file number 3. And again, I can scroll, remove, scroll, remove, scroll, and remove the last one. And now all of my emails have been filed. So according to that pattern, that means that I should be able to file all these emails without having to sort of skip over any ones and miss any. And so because I was able to sort of clear out my emails, the answer should be yes. And I checked the sample output, and it is indeed yes. Okay. The next, I'm going to go over not all of them, but most of them, because most of them are actually really helpful. The way that they set up these test cases gives you sort of some insight on how to do this. So the next one is also possible, but it's not going to be in the order of 1 to 5. So actually, now we can go a little bit more abstract. We sort of understand what the screen looks like. I'm just going to have my my 2 windows separated by a line here. And my next one will be, again, 5. So 1, 2, 3, 4, and 5. And then the file numbers that, or the folder numbers that they need to go to for my respective emails are 1, 2, 3, 5, and 4. So 1, 2, 3, 5, and 4. Again, the very first ones are following suit of what I did before. So remember, our window represents just one space that we're looking at, like this. And so I can file directly, and I can move on. So I file directly and move on. Again, file directly, move on. So these ones are removed, right? 3, again, removed, file directly, move on. Here's where it becomes a little bit interesting, because what I'm seeing now is just my folder number 4 and my email number 5. And so in this instance, I don't see this folder here that I need to place it into. And so what I have to do in this situation here is I need to move on, right? So I have to move on, and this one becomes skipped. And so now what I'm seeing is I'm seeing 4, right? I'm seeing 4, and I can file 4. And remember that property that I was talking about how we can potentially scroll up. So originally 5 was skipped, right? It was out of sight. And then I was able to file 4 by skipping it. And now I'm back up to sort of viewing this one that was skipped. It was out of sight. but now I had that resemblance of scrolling up. And now I can move down to this next one, and I can finally file this one here. So I'm sure that maybe many people got stuck on that one there. And if you didn't understand how the scrolling of the two windows works, then I think that that's probably the first place that a lot of people probably got stuck. So the next case will tell us one example of that won't work. And so let's make sure we understand the ones that don't work as well. So for the one that won't work, that will be again 5, 5, and 1. So I have 1, 2, 3, 4, 5. And then I'll have 1, 2, 4, 5, and 3. So 1, 2, 4, 5, and 3. Okay, so again, I'm going to put a little arrow to show you what's in view. Right now, K is 1, so that means I can see one file and one email, or one folder and one email. The very first ones are simple, right? I can just simply remove, scroll, remove, scroll. And now I'm in a position here where I'm viewing folder number 3 and I'm viewing email number 4. And I ask myself, well, I can't file this one directly into the one that I'm viewing. That means that I need to move on. And hopefully you're starting to understand that I want to be very careful in the way that I scroll down in this direction, because with my folders, there's no potential way that I can scroll back up, right? So once I go past 3, I'm not going to be able to go back up and visit 3 again. So that's a point that I'll get stuck. But with my right side over here with my emails, because of the way that I can file them and have that resemblance of scrolling up, it makes more sense for me to move down here. So notice that if I want to file something in file 3, I'll have to go all the way down here to get it, which means that I was skipping over these ones here. Okay, so if I were to move down here, then I can file it, which would be okay, right? Because I file it, I jump back up here. But then there's an issue of, okay, well, I'm at email 5, right? Or not email number 5, in the email that needs to go in folder 5. But in order to do that, I would have to move all the way down to 5 in order to do that, right? So we have that movement here, which means that I had to skip over this one. And so even though I'm able to file this one and I can finally move to my last email I need to file, there's no way for me to jump back up to this one here. And so in that case, I'm stuck. So for hopefully that makes sense why this one is a no. I won't be able to jump back up in my folders. Remember, I can only potentially jump back up with my emails. So to sort of spare us the time, I know sort of take a long time to go through the test cases. Hopefully we can catch on to some patterns that are really important in this problem. And actually, let me draw that last test case there so we can sort of see what those patterns were. So I had 1, 2, 3, 4, and 5. And then I had 1, 2, 4, 5, and 3. 1, 2, 4, 5, and 3. So again, one part that I noticed I got stuck on was when I was viewing here, and I was viewing here, I realized that I would need to go all the way down here in order to file this one across here. And if I had a 3 that was even further down, I would have to scroll even more. I would have to go further down. So what I'm noticing is for these files here on the left side, an important piece of scrolling information is asking ourselves, how far down do we need to go in order to touch that last file that needs to go in each respective folder, right? So let's examine that. So this is going to give us sort of our building block for our answer here. So in this case, for 1, how far down do we need to go on the email side in order to make sure we file all the emails that need to go to folder 1? Well, this is as far down as we need to go, right? it's within my window, so that's not an issue for me. How about for this one? So for this one, again, similar to the other one, I don't need to go further down, right? I'm going to have everything in my window, so that's not going to be an issue for me. When I get to 3, this is my one that became a problem, right? I realized that in my window, I was looking at 3 and 4. Is it, I'm seeing something, is it possible that 2 emails get filed in the same folder? Yes, it is possible that 2 emails get filed in the same folder. Actually, I can go over one of the last test cases are interesting, where we see like emails going to the same folder. So let me just finish up this one and I'll show you one with the one where we have 3, 10, and 1, and we have lots of 1, 2, and 3s. Okay, so we realize on this one here, we need to jump down all the way down here, but that's outside of my window, right? I was originally here. And so since this is going to overflow my window by trying to include this furthest away 3 that needs to be filed, this is going to be an issue for me. And so that means that I'll have to do a skip. So if I'm going to have to skip items, right, I'm going to have to, mark them as skipped. And if I mark them as skipped, then my only way to try and catch skipped emails again is by our resemblance of scrolling up by, filing emails that are further down along the line, right? So what we can do is we can check, see, hey, is the one that I need to file, which is the furthest one down, which matches the current one that I'm at, is that outside of my window, right? Does that overflow my window? If the answer is yes, then I'll need to skip the items above. So I'll skip items above, and you can mark them. You could have some sort of vector of all your skipped emails that you have. And once you do that, then we have our last step, which I showed, which is to say, okay, I've skipped these ones, but let's keep moving down, right? Let's keep moving down. So I have 4 and 5, and I can do that same process. Okay, where's the lowest level one that I need for each of them? Is that within my window? And keep asking yourself, okay, is the furthest one down outside of my window? If the answer is yes, that means I need to skip the ones above my position, and I'll add them to some sort of list, or you mark them in some way that you're skipping them. And what you'll do is you'll have that list, okay? And like I said, we have to have that process of moving back up. So it's not so simple as saying whichever emails, if I end up skipping an email, that means that the solution is impossible, right? Because we saw in the example here, we had to skip over these ones to file this one down at the bottom. But, we were able to jump back up to this one here, and, we were able to move down to 5, and we were able to file this one. So be very careful. You don't want to have that impression that, skipped emails means that the solution is impossible, because we have to still simulate this process. Okay, and like I said, let me show you that one where we're filing multiple ones. I'll try and do it relatively quickly. So it was I'll do the last one, 3, 10, 1. So 3, 10, and 1, 3 folders, 1, 2, and 3, and then 10 emails. So I have 1, 3, 2, 1, 3, 2, 1, 3, 2, 1, right? So again, keep track of my top, I have 1, so that's my view. File, so file, move on to the next one. Again, I'll need to skip, so I can skip, right? And I'll go to 1. And the first one was a 1 actually. So this is an example of me filing another 1 in that same 1 folder. And yeah, you can see that I can continue down, and these 1s we're going to file in the folder, and the 2s will go in the 2s and the 3s will go in 3s. If you test it out and follow that same process that I showed you, you'll see that when we have a window of size 2, it is going to be possible because you'll be able to shift up the window and always make sure that you have one of the items in there you can move to the other side, while the other one you'll not be able to do that. Okay, so in summary, what we need to do is we have our folders, right? Our folders from what were they, from 1 to M? Yeah, M and M. So we can loop over all our folders from 1 to M. So this is the important part. So 1 to M, we'll go over. And as we're going over our folders from 1 to M, what we'll need to do is we'll have to examine what is the farthest down email that needs to be filed in each respective folder. So for example, if I'm starting at 1, I'll check my email list. I'll go to the furthest one down that needs to be filed in folder 1. And I'll check to see, hey, where's my window? Is this outside of my window from this furthest one? If that's the case, then I'll need to skip the ones above, and I'll need to mark them as skipped. So maybe you make some sort of vector or something that says skipped. And once you do that, then you can file just make sure that you maybe have some vector or something where you file all of these, and then you move on to the next one. Then I go to 2 and check which is the second furthest one down from 2. And then at the very end, once you've done that from 1 all the way to M, checking to see the window and making sure that the furthest one is inside the window. If it's not, we mark the top ones as skipped. What we'll do is we'll again simulate this process of moving back up the chain by checking our window, seeing if the email within our window can be filed. And if so, then we can remove those skipped ones and get closer and closer. And then at the end, if we still have skipped emails in the very end, that means that it's impossible. If we were able to remove all of those skipped emails, then we know that the answer is possible. So yeah, that's how the problem works. It's a simulation problem, and the code is a little bit long, so you can go to the USACO website to read it and sort of study it. But I think the more important part is to, how do we remove skipped emails again? How do we remove them? What do you mean by remove them? Like we don't want, we don't remove the skipped emails, remember? So if we have our list of emails and they're here, and here's an email and it doesn't fit, within my window, so I need to skip it and move on. I just want to mark it as skipped. It still needs to stay in my email list. I don't want to remove it from my email list because if so, then I'll mess up my ordering. And also, if I remove it from my email list, that's kind of the same thing as almost filing it. Well, in the list here, if it's gone from here, then it almost looks like it's filed. So make sure you don't remove it from the email list. Just mark it like I did. I put it in a vector of the ones that are skipped, and that way you can keep track of them. When do we come back to the skipped ones? That's at the very end of our simulation process. So once we've simulated going through all the 1 through M values here and going down to the very last one for each one that needs to be filed for those, then I can have a loop where I'll go backwards up through my chain here. So I'm at the end here. You can see my last window, and I'll do exactly what I did when I was simulating that process of checking, I have my window, here's what I see in my window. Can I file it? If the answer is yes, then I move this email to the filed list. and I can move back up the chain. So another important thing that you'll have to keep track of along the way is, so like I said, you have to keep track of the topmost folder as you're going through, and you also have to keep track of the emails that we've filed, I'm sorry, the skipped emails. And in order to that, we also have to keep track of the earliest point of time where the email can be filed. So just make sure that you have all those pieces together and simulate the process. You could potentially write a good amount of code, but I think that's pretty much expected nowadays with silver level problems to write like more than 50 lines of code. So hopefully that was helpful. And yeah, let me stop my share and I'll send it back to Maggie.
All right, thank you, Brendan. So that is the end of our workshop. Thank you so much to all the teachers for your great presentations, and also to XCamp for helping us host this workshop.